paper there of equation 12, I think. Um, and this really goes to answering Ethan's question of like, what do you not just go if you do gradient descent on some potential energy? Do you not just always go and get stuck at the bottom of the well? And well, you would. So you need to add noise. So like what this is like an equation for an iterative gradient descent, but on each iteration, you don't just go in the line of steepest descent, but then you also add a little bit of noise. So if you're familiar with different like optimizers, it's like stochastic gradient descent basically, or SGD. But this is actually from the paper SGHMC, which is like a kind of stochastic, optimizer basically. But so people have used that in one way. One reason people use that is because it helps you get out of local minima or whatever is the idea. But the other reason to use it is that it's actually you can actually think of it as a Monte Carlo algorithm for sampling from a distribution instead of just like getting a point estimate of the minimum, basically. So that's like, so this is, you see this a lot in energy-based models that people sample from them by running like stochastic differential equations like this. And the reason why is that if what you have is the energy, that's the like the u of theta, this equation. And so if you have that energy function, then it's really natural to use it in your like iterative like optimizer, basically. But yeah.
But it seems to me, so it's sort of like a bit of a it's a proper naming if you talk about it for a particular snapshot, but it's a misnomer, or it's kind of a sneaky way around. It's kind of the opposite, right? Because you're, in this sense, especially with the deep connections to thermodynamics, noise is actually, you could speak of it as energy or different errored information back into the system. But you kind of have to do this repeatedly, right? So on the bigger picture of what's perhaps going on is then it's kind of a misnomer, or maybe you talk about this being like metabolism, right? It needs, it's
Are you
not
saying
just
that, like the energy-based model term is a misnomer, kind of?
maybe not energy based, but
Okay.
like energy minimization. Often I hear about it.
Oh, I see. Yeah, in
But
that case,
energy
that's
based, I don't have that I don't have a problem with,
I
because
see what you're
that's
saying. Yeah, that's absolutely true. It's really what's being minimized is free energy, not energy. And
right.
if you just think of it as like free energy minimization, then it comes into perfect kind of alignment with the statistical physics and with what's really going on. I think. Yeah,
Okay.
yeah. Because like the when for the energy to be minimized, yeah, you would have to be at like some very low energy state, and that would be like a perfect, like kind of a deterministic, state. Like
Hmm.
it would have zero entropy. But if you try to minimize free energy, that's more like saying, okay, I'm going to minimize the energy with respect to a constraint that there's a certain amount of entropy, or
Hmm.
find the distribution with the same kind of spread or entropy that has the lowest energy, and that's like more so what actually happens when you run these like Monte Carlo simulations, basically.
But even there, you also still have to keep sort of introducing a metabolism, or you just have to keep introducing noise over and you have to keep perturbing the system, right?
Yeah,
If
you
you
have
want
to keep introducing
further,
noise. Yeah,
yeah.
yeah. I'm not as familiar with the term like metabolism, but yeah, you do have to keep introducing noise, which in thermo that corresponds to a heat reservoir. So like
Mhm.
when you have some system that's coupled to a heat reservoir, the you can often model it using like a Langevin equation, which
Yeah.
really looks exactly like this equation 12. Uh,
No, and what I meant by what I was saying by metabolism is just like, if you make analogies to brains or living systems that exhibit them, supposedly perhaps some shared thing about explaining, neural nets work. Well, they have them, they have to keep getting energy. They have to have a metabolism, right?
oh, I see what you're saying. That's like the energy input to the system, kind of
Yeah,
somehow.
which is, yeah, but it
Uh,
also, if it's a
Maybe a
constant
source term.
perturbative yeah, I don't know.
Sorry, someone added something.
Yeah, Max,
Yeah.
are you referring to a source term? Is it the gradient source term, or I'm not sure what the metabolism is.
Well, so
I'm
I think like
still.
Ethan was saying that like without that noise term, the energy always just decreases for this equation because you're doing a gradient descent on the energy here. So it's like a very damp system.
And
And
same with
without
free energy again too, right? Even there you
yeah,
gotta, it'll happen.
right.
So
So
do you?
when you look at like modeling a system that has energy inputs and outputs, like, well, you could think of a living thing, or you could just think of something simple like a heat engine, right? Then it's for exactly what Ethan was saying. It's not just going to look like this equation, at least as if the equation isn't changing over time. So one way that energy comes in is through heat, which is that noise term. But the other way that energy comes in is through work. And the way that work is done is by changing the potential energy function over time, actually. So like if you run this with one potential energy function that stays the same, then it will just go towards kind of the minima of that potential energy function. But if you change the potential energy function, that kind of corresponds to doing something like moving a piston in and out of a box or something, like, changing the container that a gas is in, basically. And that's the way that work is done. And I think that what like Ethan's talking about as a metabolism is closer to the second one, actually, like useful work, because heat actually isn't something we can't just like absorb heat from our environment and use it to do useful work without running some kind of heat engine cycle. But if you think of like something like a battery, or like how food is somehow some kind of chemical battery, it's more like work than like heat, I guess. Yeah.
So the work is against injected noise and friction. Which one are you referring to when it comes to like work against what in analogy?
I wouldn't say that you don't necessarily have to think of the work as being against one of those things. The way I'm thinking of work is in the sense of the first law of thermodynamics, that du equals dw plus dq. There's basically this overall balance of energy where a system has a certain amount of internal energy, and that internal energy can change in one of two ways: through doing work on the system, or adding heat into the system, or conversely, like the system doing work or taking heat out of the system. So yeah, that's really just what I mean by work, is that general sense. It was a way of putting energy in or taking it out of something.
So in that equation you sent, the d theta is negative m. And the u function there, is that a distribution, or is that something else?
So that is like more like the log of the distribution, of the unnormalized distribution. Okay, so if we go back to
Log space non-normalized.
the book, right? So if we go back to chapter 24, page 845, equation 24.1 in Murphy's book is the relationship between that u function and a distribution. So if you see like the script e, the script e sub theta, that plays exactly the same role as u. You can think of that script e sub theta and the u in the other equations being exactly the same thing. And so it's like a way of parameterizing a distribution, basically.
Page 850?
845. Or at the beginning of chapter 24.
Oh, okay. Cool. Perfect. I got the book now.
Yeah. But let me screenshot that equation also and put it in.
Sorry, are we on? I should probably clarify. Are we on book 1 or book 2?
Oh, book 2, advanced topics.
Okay, and 845 you said. Oh.
So it says p theta of x equals e to the minus e theta of x over z theta.
All right, I think I'm with you now. I think I got it.
Okay. So yeah, okay. So basically, yeah, I think this is a nice way to start to talk about EBMs, is that like if we look at equation 12, this is like a dynamical picture of an energy-based model, like how the state is changing over time. And if you use these dynamics, then it'll allow you to sample from the stationary distribution. Kind of after enough time of running that equation, you'll get to a stationary distribution. And then equation 24.1 in Murphy's book is the other picture, more kind of the definition of it, which is that like the energy is the negative log of the unnormalized distribution.
So how? So you're saying that's like the u function in the first equation you sent, or?
Yeah, exactly. The e theta is the u function in the other equation. Yeah.
U theta. Oh yeah. Okay. Gotcha. Yeah, that makes sense. So I have a question about this because in physics, it makes sense that you might have like some external heating resource, which is kind of how I'm envisioning this equation. That you said that like you've got your Lorentz distribution and then you've got your modifier distribution. I guess is there an advantage for keeping that in I guess like in the realm of using these tools to optimize like functions inside of computers? Like, does this equation have an advantage over say like not having this like external cooling or
Yeah,
like heating?
I mean, so absolutely. So one of the big reasons to do this is just the kind of mathematical detail that it turns out that the partition function z, that normalization factor, turns out to be something that you can't like. It's really hard to compute. Like a lot of times, you have a distribution that you have it in a form where it's not normalized, but it's just hard to figure out what the normalization factor is. Because in order to figure out the normalization factor, you'd have to do an integral over like a very high dimensional space, which is not not really something you can do. So that's one reason. Another reason is that well, when do we expect this treatment to be useful? When do we expect it to be nice to talk about the log of something instead of the thing itself? Well, usually if you're going to multiply a bunch of things together, it's going to be bad to talk about that product itself, but the log of that product will be easier to work with. Because when you multiply a bunch of things together, you kind of lose a lot of precision, and you get really big numbers very quickly. But if you're talking about the log of the things you're multiplying together, that maybe a lot better behaved. And that basically happens if you have some distribution, and then you want to condition it on a bunch of other on a bunch of data. So, like for example, if you're thinking about like using Bayes' rule, where p of like you want the posterior p of y given x, and you do that by multiplying a prior p of x and the likelihood p of x given y or whatever, then you could actually be conditioning on many things. And so you would have like one prior, and then you multiply it by a bunch of likelihood terms for independent observations. And then you would have like your distribution you want to sample from is a product of many, many things. And so that's exactly the kind of situation where it's nice to use the log of the distribution, I think, just for kind of numerical reasons.
Yeah, absolutely. Yeah, it's so much easier to work with distributions that are in log space than in like continuous non-log space. Like just for computers, because I ran some like tests of trying to do it in not log space. So like running basically like, trying to train like a theta based probability distribution that can optimize some random function. And I like watched the spikes. I plotted the actual distribution itself, like the outputs, and like it's really hard to get any values out of really really low uh, a really low standard deviation value function or like distribution. Like, but when you compare that to log space, it's so much easier to get very high certainty models or like distributions, um, just because of the floating point precision at more normal levels of log space.
Interesting, cool. Yeah, maybe could you talk a little bit more about like what you were building or like what the application was, kind of?
Um, well, the function itself that I was running was I can't remember what I was actually optimizing. I think I was just trying to plug in. I was just plugging in values because I had some suspicions about reinforce and its stability inside of like once your model your agent becomes really 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 high certainty, so low entropy. Um, there's oftentimes a collapse in its performance. This is something that's observed by many different like RL problems and stuff. But you get something called like performance collapse, where the model stops. It basically like overfits, but then it gets like way out of whack. Um,
So is that the same as saying that it memorizes and then can't be creative anymore?
um, no, well, I don't know, but
It's worse than that.
if you I don't really know what the agent feels like when it's being trained, but what you can observe is that the loss values or like the reward average over time will start to like go kind of crazy. But basically, I had a hypothesis that if you were to get really, really high entropy, it would become, or like really, really low entropy, really, really high certainty. So really, really low sigma value for the